equal functions two functions f and g are said to be equal if they have same domain and fx same domain d. F of x is g of x for all x belongs to domain. So let us see few examples. F of x is x, g of x is generally what we do is we cancel and we write x. Cancellation is allowed if x is not equal to 0. So here, as it is, if he gives this, it is not defined for x equal to 0. So here, f is defined for x equal to 0, whereas g is so no value for it, not defined for 0. So f and g seems to be same, but they're not having common domain. Hence, f and g are not equal. Example number 2, f of x and g of x is defined. This condition is satisfied. Suppose if I restrict domain of f to this, domain of g3, g2, 1 to 3, your function will be when x is 1, f of 1, 1 square. When x is 1, it's 1, 2, here you have 4, 3, here f and g are not equal. They define same way, but their domains are different. So functions are not equal. So another example, f of x is log x square, g of x to. In general, what we write is log x power n is n log x. That is not true for all x. For example, x is minus 1, log minus 1 square log 1, 0. But g of minus 1 not defined. Log is not defined for negative numbers. So if x is not equal to g of x, since their domains are not equal. Right. Finally, conclusion is for equality of function, domain of f. Second, fx is g of x. for all x belongs to D. Next, composite function. This last class I discussed once again. F map from A to B, G circle F will, this is circle, G circle F map from A to C and defined as G of F of X. Now, F map from A to B, G map from B to C are two injections, then prove that G circle F map from A to C is 1 1. Injection or 1 1 function one and the same. So whenever you are proving a theorem, you should write what is given. These are two 1 1 functions required to prove is G circle F map from A to C. Proof. G circle F means here first you should start with F, not with Z. F map from A to B, G map from B to C. G circle F map from A to C. Right. So write that clearly. F map from A to B, G map from B to C. Then G circle F map from A to C. So how to prove that one function is 1 1? To prove some function, any function is 1 1, you have to assume G circle F of x1 is G circle F of what are x1? X1 is in domain of F. This is assumption. Finally, you have to prove x1 equal to x2. So then we say that G circle F is 1. By definition of composite function, G of F of x1 already what he given is in the given information G map from B to C is 1 1. G map from B to C is 1 1. That means we can write F of x1 is, so basic definition of any function which is 1 1. H is 1 1 means once if at all images are equal, elements are equal. Now, which implies again x1 equal to x2, since f map from A to B also 1 1. So I assumed G circle f of x1 is G circle f of x2, and I concluded that x1 is x2. So from this I can say G circle f map from A to C is 1 1. This is how you have to prove the theorem. And in this class, I will explain one more theorem. F map from A to B or onto. Sometimes they use a word subjective. Then G circle F from A to C is also onto function. But before proving proof, given you should write F map from A to B or onto functions G circle F map from A to C is also onto. Here F map from G circle F means start with F, domain of F. So how to prove one function is onto? Say here, for example, three has pre-match, four has pre-match, but five is not having pre-match. G is not onto. When it becomes onto, when you remove this five, so for three you have pre-match, for four also you have. That means what I have to write is for each element in B, there exists pre-matching E, right? So that means to prove G circle, some elements I have to take here. For that element, I should find pre-match. If I can find pre-match, it is onto. I'll take the help of given condition. G map from B to C is onto. That means here C is an element belongs to capital. I wrote a big letter. It is a small element. I should write small letter. Set I should write capital letter. Since already mentioned that G is onto, there exists B in B such that F map from A to B is on to for B belongs to B. There exists such that so now what I have G circle F of A will consider G of F of A, that is G of B. G of B is G circle F of A is C means C is any element which implies for C belongs to C. There exists A in A such that G circle. So for any element in codomain, there is pre-image in the domain. Therefore, G circle F from A to C is on to function. Another theorem, F map from A to B, G map from B to C are bijective functions. Then also bijection. So here it is. First of all, bijection means both 1 and on. Whenever he asks theorem 1, first assume that F map from A to B are 1. So G circle F map from A to C 1. So it is theorem 1 proof you have to give here. So it's a bijection means it is on to. These are on to. Then G circle F map from A to C is on. Theorem 2 proof must be given. So by writing theorem 1, theorem 2 proof here, we can say finally it is G circle F is both 1 and on to, and G circle F is bijective. Right? Don't write only this statement. You have to write complete proof of the first theorem. So in the next class, I will discuss